And our next speaker, you also probably know, I guess you've seen his science paper last year on HIV, but he's not going to talk about HIV, I think, today. He's going to talk more about SARS CoV-2 and some more public health and epidemiological modeling. So, Chris, happy to have you, and the floor is yours.
Thank you. Yes, I'm Chris Wymant. I'm a postdoc with Christoph Fraser at Oxford in the Big Data Institute, and now in the new Pandemic Sciences Institute as well, which is hosting a conference in July. I'll be presenting unpublished analyses of data from our national COVID contact tracing app, which is not public data, and we're allowed to discuss these results with other academics, but it has to remain in the room. So please don't take photos or record or do very accurate drawings of our plots. So manual contact tracing is familiar in infection control for different infections, respiratory, sexually transmitted. After a case is identified, they're interviewed and asked to identify people they might have infected based on their memory of the exposure event. And for COVID, heuristics like 2 meters distance for 15 minutes might be used. And then if the index case has details for those contacts, they can be contacted by the tracing staff. And requested or legally required to do something to reduce their risk of passing the transmission still further, such as quarantining or testing. So this reduces transmission. A byproduct of this process is generating data that informs transmission risk factors. So we get that if we record data about the exposure or the people involved in it, and link that to the later outcome of whether the exposed person tests positive or not.
Chris?
When we identify transmission risk factors, that's useful beyond the tracing intervention. It's useful for other interventions too.
Chris, I'm really
sorry. Digital contact tracing is doing contact tracing using smartphone apps. The basic idea is just that if two smartphones that both have the app installed get close to each other, they record that fact. They estimate their proximity using Bluetooth signal strength, and they record that they were close to each other and remember that for a little while. And then if one of them later reports a positive test, the other one can be notified of the risky exposure if analyzing that exposure indicates that it was risky, that it was close, it was long, etc. So that's the basic idea. This reduces transmission in the same way. We've shown that in some previous papers that I'm not going to talk about today. So 3 years ago at this meeting, I presented our initial proposal based on modeling, and then we then did an actual evaluation of the intervention. You can read about in the papers here. There's also a recorded webinar on my webpage. So it reduces transmission, but it's hard using this intervention to understand the transmission process. So the implementation for this has mainly been done through the framework Google and Apple embedded in their mobile operating systems for doing this. And it's done in a very privacy preserving and data minimizing way. In particular, it's called a decentralized system. Meaning that when two phones get close to each other and sort of notice each other's presence, the only places that data ever exists is on the two phones themselves, not centrally. So that makes it very hard to analyze not just the intervention, but to learn about the transmission process in the way we're used to doing for manual contact tracing until now, when we've managed to do a first analysis about that. So I'll be talking about the NHS COVID app for England and Wales. I'll first explain the risk score calculation, so how it decides who should be notified of risky exposure and who shouldn't be among everybody with any level of recorded exposure to the index case. So that risk calculation is done separately in 30-minute windows. So that's quite important for the rest of the talk, so keep that in the back of your mind. So for example, if there's an hour-long contact event, that's just 2 separate windows. So in each 30-minute window, the risk score is calculated as the product of 3 factors. So the first factor is a proximity score calculated from the proximity, which is estimated from Bluetooth signal strength. And that score is constant at distances below 1 meter and then declines quadratically at greater distances. The second factor is just duration, anywhere up to 30 minutes. Longer than that, and it would be in a different window. And then the final factor is infectiousness of the index case, which is just encoded in 2 different levels. It's taken to be 2.5 times higher in the few days around the index case's onset of symptoms, or when they reported their test if they didn't have symptoms. So the product of those 3 things defines the risk score for the window. There's an overall scaling constant, which is arbitrary because this is just compared to a threshold that's calibrated from manual contact tracing. And then if a contact has at least one window with a risk score over the threshold, they get notified. Or equivalently, if the maximum risk score among any of their windows is over the threshold, they get notified. So we managed to put together a data set about those risk scores. It's only for people who were actually notified, not for everybody who was below the threshold. There isn't time in the talk to explain how we put this data set together, but I'm going to illustrate the format of the data using completely fictional example for 3 contacts, C1, C2, and C3. So we have no data about the index cases that these contacts were exposed to, except for this binary, this one of 2 levels of infectiousness, 2.5 times or 1 of the baseline. So no data about the index cases, but we have the for each of these 30-minute windows that was individually over the threshold for notification. So only one of these would be necessary for notification, but in general, a person can have more than one. So for each window over the threshold, we have the overall risk score, and then we have the 3 factors that multiply together to give that risk score. The proximity score, the duration, and the index infectiousness, and we also have the date of exposure. So all of that data is per window, a 30-minute window, and we also have data that's per contact, namely, did they report a positive test through the app in a time window starting from notification and ending 14 days after exposure. So that's just how the data works. This isn't some outcome we thought it would be useful, sort of interesting to define in that way. That's what we can get from the data. So I'll go on to talk about probabilities of infection and probabilities of transmission. These are going to be underestimates because we're using this observed outcome of a reported test in the app in this time window as our proxy for whether someone's infected or not. So there's strong under-ascertainment. So that's the form of the data. And we have this for 7 million people who were notified through the app in England and Wales, together comprising 23 million hours of risky exposure. So the natural question to ask of data of this format is, does a given contact's collection of measurements about their risky exposure predict their outcome of testing positive or not? So for example, for C1, for this red contact, this data in the red rectangle on the left, for the 3 windows this contact had, do those set of measurements predict the red outcome on the right, that person did test positive? So the first analysis we did to address that was just to simply summarize over all of the windows a contact has some summary metrics for their exposure. So the first of the 3 we calculated is their maximum risk score. Do I have a pointer? Yeah, so we summarize over their risk scores, the maximum risk score, so here that's 8. And then we also calculate their cumulative risk score over these windows. So that's adding these together, 14. And then the duration or cumulative duration over all of their windows. So for here, that's 75 minutes. So we calculate each of these 3 metrics for every contact. And then we simply group or bin the contacts together based on the values of these metrics. And then within each group or bin, we just calculate the fraction of them that reported a positive test result. And we call that the observed probability of infection, but remember, it's under ascertained. Here are the results of doing that. So to begin with, just look at the top row of plots. So there's 1 plot for each of those 3 summary metrics. I just mentioned each point on the plot is 1 bin, and the lines just connect the points to ADI. This is very smooth, not because we've fitted some smoothed parametric function to noisy points, but because the points themselves are just extremely smooth because there's 7 million observations shared between these points. So what these plots are showing is that as these app-measured risk scores, these summary metrics for whole exposure, as these predictors go to higher values, a bigger and bigger fraction of individuals with those values test positive. And then the bottom 3 plots show the same thing again, just disaggregating by the month of the exposure. And you see the same kind of thing, except what becomes a bit clearer here is that as you go to the lowest recorded values of the risk predictor, so as you go to the left-hand edge of these plots, the fraction of people testing positive doesn't tend to 0, but it tends to some background rate. So people could have been infected by someone who wasn't the index case that caused them to be notified. And that background risk level varies, of course, with the different waves of the epidemic. So you see it's different for each month. Then we estimated the background risk for each contact separately in the whole data set. I'll say in a minute how we did that. and then we subtracted that background risk probabilistically such that within each bin of contacts, the remaining set of positive tests can be attributed to the recorded exposures rather than to the background. So we call this the observed probability of transmission rather than infection. And now as we go down to the lowest risk scores, we see this thing does go to 0 because we've removed the background that was there before. It's shown here on a log-log plot. And at the lowest values of the at-risk predictors, this relationship is linear, which makes sense from kind of mechanistic understanding of the transmission process. And then at the bottom, this is showing the distribution over contacts of the values of these different summary metrics we've calculated. In blue, it's over all notified contacts. And you can see it's very left skewed, even for people who are notified of risky exposure. It's much more common for it to be a not very risky exposure, relatively speaking. And then in red is showing those metrics for transmissions. So for contacts it's contacts who've tested positive after the background risk has been kind of removed. And you see that those distributions are shifted towards higher risk, as you would expect, given that, given the causality of higher risk causing transmission. So these results match our intuition, which is that an individual's overall level of risk is set by having many windows, i.e. a long duration of exposure. It's set by those windows being riskier, so closer, basically, a smaller proximity. And if the background risk is high as well. So those three things combine to give the overall risk. And so to disentangle them and to estimate their separate contributions to overall risk, we used a likelihood for who tested or who reported a positive test and who didn't, given all of the exposure data. So I'll just talk you through that likelihood. It's the product over individuals. And for individuals who didn't report a positive test, so sort of negative or just didn't report a positive test, the factor they contribute is given by 1 minus the background risk, big B, and we modeled background risk as being effectively proportional to, just accounting for saturation, that's this term on the left, effectively proportional to the per capita incidence in non-notified app users. So everything else I'm talking about is app users who were notified, but in separate data, we know something about app users who weren't notified. So we use the per capita incidence at the time and place of the person we're talking about in non-notified app users. So that's sort of how we model background risk. And then we have the product of 1 minus the probability that a given window caused transmission. And we multiply that over all of the windows. And the probability that a given window caused transmission, we modeled as a function of the risk score recorded for that window. And then we don't know what that dependence is. So as this risk score changes, how does the actual probability of transmission change? So this is what we want to estimate. And we model this as a piecewise constant function, as I'll show in a moment. So the overall form of this, as you can see, is 1 minus the probability of transmission from something, all multiplied together, because these are people who haven't tested positive. So we need all of those transmission things to have not happened. And then for people who did test positive, the contribution to the likelihood is just 1 minus that whole. So here is that piecewise constant function I just mentioned. So to begin with, if you just look at the points, so these points are showing the observed transmission risk for a 30 minutes exposure window attributed to that window, not to a different one, not to the background risk, as a function of the risk score that the app measured for that window. So there's nothing in our modeling assumptions that means these things should be proportional to each other, but they are. So what that's saying is that in a given 30-minute window, when the app records there as being twice as much risk, there actually is twice as much risk of transmission having happened. So this is an incredible validation. Then just to say the line is robust regression fit to those points, just to highlight the proportionality. And then the saturation on the right is a bit complicated to explain. I won't go into that. But so if I just flick back to the risks who I presented, so the second factor duration, probably everybody would have said, yeah, it should be proportional to duration on that timescale. 30 minutes is twice as risky as 15 minutes. The infectiousness factor, I think, doesn't actually end up playing a big role because sort of most of the data set is within that window around exposure. But the proximity factor here, reasonable minds could definitely have proposed different factors for how does your actual biological risk of transmission vary according to distance. And so having used this factor and then kind of looked at the empirical validation, this is really reassuring that this is capturing when, how much risk there was in that particular. So I've deliberately kept it short and leaving time for questions. I won't read out the takeaways. I can just leave them here during questions, except to mention that there's an extra slide looking at the balance between sensitivity and specificity, as we could imagine changing different thresholds on different metrics. So thank you to the co-authors, the app team, the app users, the Lee Cushing Foundation, and the Department of Health and Social Care for funding. Samuel already kindly mentioned this paper. I presented this 3 years ago, and this was published last year. So these the app evaluation papers and this paper, there's webinars for both of them on my GitHub teaching page. Thank you very much.
Thanks a lot, Chris. Lots of questions.
So thank you, Chris. I mean, you showed very clearly that this is an approach that works, but how easy is it to implement this knowledge now when, at least in Sweden, we stopped a large-scale PCR testing a year ago? Not even healthcare workers are allowed testing if they have symptoms now. And so the only PCR testing that is done is for persons admitted to healthcare for symptoms. Mm-hmm. And then antigen testing has also dropped dramatically, sort of private initiative antigen testing. Of course, the knowledge that this works is very important for the future, but how do you see that it's useful right now?
Yeah, so in terms of how easy, I mean, there's different things you can do with these results, right? So in terms of seeing this as the first of a number of analyses, in order to do further analyses, we would need more testing and we would need more people actually using the contact tracing app. The English and Welsh app is being decommissioned this month, I think, and I assume they are in lots of places. So that doesn't give great potential for doing massive scale sort of population level analyses. But, you know, hopefully we can continue doing smaller scale studies because, you know, my last takeaway here is we should get better at both sort of understanding how to make this work well as an intervention and understanding how we can learn more about transmission through doing this. We should try and get better at both of these before the pandemic. So hopefully on some smaller scales, we can continue doing these kind of things. And yet testing is needed for that. And in particular, if you're going to do a dedicated study for this, rather than just, you know, use, I forget what the term is, but like observational data that happen to exist, it would be nice to test everybody instead of just relying on some people to choose to test. So that's part of it. And then in terms of using this, even if we don't have any testing in place, once we learn about transmission and risk factors through this intervention, it's useful beyond the intervention. So, for example, we showed that I forgot to mention when I put up the slides, I'll perhaps put it back up. So here we see that the fraction of people reporting a positive test as a function of duration, the top right plot, continues just increasing even after several full days of exposure. So, you know, what we take away from this is that, for example, household transmission isn't a given. Once somebody in your household tests positive, you don't think, oh, well, I've definitely already got it. Even if you had 2 full days, you know, maybe you still haven't got it. So there's things we can learn about this, even if people aren't testing, just by understanding the process.
Hi, that was really great. So I'm wondering, I guess the way I see it is that the digital contact data feed into effectively quantifying or helping you quantify kind of transmission rates almost, right? But you have that other part of it, which is the outcome data, which also depends on the susceptibility of an individual, right? And that susceptibility of that individual might depend on their previous infection history, their vaccination status, et cetera. So, and the digital contact data, you know, so the outcome tells you something also not about just their contact with someone who's infectious, right, which is where the digital contact data is feeding in, but also is impacted by their susceptibility, right? And so I'm wondering, in terms of identifying kind of the risk factors associated with transmission, is that variation in susceptibility that's also impacting outcome? Do you think of that as just like noise or time varying noise, or how do you deal with that basically in terms of identifying your risk, your drivers or the risk factors?
Yeah, so the extent to which it's time varying would be visible in the bottom plots here. Otherwise, this is basically noise for us because we know nothing about it. So because this is so privacy preserving, the level of information we have on each person using the app is their self-declared postcode district. So it's just which isn't a particularly, well, it gives you some idea of where they're living, and they've self-reported that they're over 16. And that's the extent of what we know about each person using it. Going back to this point about doing smaller sort of dedicated studies, that would be great information to link to this. And of course, if people have, opted into a research study rather than just said, yes, I'll use this to stop the pandemic, they might be more willing to volunteer extra information. But for this analysis, we just don't know. And it's an average over all of these things.
Okay, I think we're going to have to finish the questions here. Thanks again, Chris.